I'm recording now, I think. Did I make that happen? Pause, stop, okay. So if we have natural log, again, you're integrating, and like in this problem, we get it set up so that we can take this 3 plus 1 x, factor out 3, and then finally it's in the form of 1 over 1 minus x. Once you get something in that form, you can directly take this negative x over 3, raise it to the n, and put sigma. And then this is the problem where we then integrated, put our c, we solved the original function by plugging in x equals 0. You get ln of 3, and that's your c value. Everyone, worst case scenario, if you get a function and you're like, I don't know what to do with this, but you need a series, worst case scenario, you could try the chart. So like you could set up and do function, take the derivative, plug in whatever, you know, it's centered around. So you always have that as a backup. But again, you kind of want to cross-reference, like, you know, which section is this problem from? So then we head into Taylor and Maclaurin. So Taylor and Maclaurin, again, here's your intro to Taylor, where we use the chart. We took the derivatives, we plugged in 1 because it's centered at 1. We did that over here. And then everyone, you have your formula where you plug all these values into the numerators. Once you get it written out, then you can write it in sigma form. So that is your process that you always have as a fallback to fall back on. This is e to the x centered at 0. So now you don't need to show this work because we do have the handout. If it's centered at 0 and it's one of the familiar functions, then you have your 9.10 handout. So please have that obviously for a quick reference during the test. Same thing here, sine of x centered at 0, just use the handout. And then that leads me to these application problems. So now that you have the handout, you can then manipulate, or you have sine of x over x, and then you have an integral. So when you have a composition, use the handout. When you have a product, use the handout. Because taking derivatives of a product and then keep taking the derivative is going to get really messy really fast. So there's going to be problems like this on your test. Same thing, this is a composition. So we're using the handout and then we're plugging into x for x. Also, this one is unique. You have x to the x, or e to the x squared minus 1 over x. So this guy we can generate from the handout, and then you take the entire series and you subtract 1 and divide by x, subtract 1 and divide by x. And so the ones cancel, and then you divide all these terms by x, so you get the series you need. So again, it's manipulating using the handout. Same thing here, the coefficient of x to the 4th, and then here's your function, use the handout, and then plug in for x, and then look for the x to the 4th term to find its coefficient. And then finally, 9.10b, where is it? 9.10b notes. We're talking about Taylor polynomials. So it's basically the same thing. When we have 1 over x, again, this one you use the chart, plugged in, this is centered at 1, went straight to the series. And here's an example where we use the chart. You take the derivatives, you have ln of 3 minus x, and it says it's centered around 2. So if it's centered about something, you're not using that handout anymore. You're using your derivative chart. This is a common problem, so please, if you guys have any questions about this one right here, please ask. It's very similar. It just gives you the values, so you don't have to make the derivative chart. Do you guys see that? And so you just plug these in into the numerators of your Taylor formula. So this is very common that I've seen. Also, this is a common problem. Again, if anyone has a question, please ask. It says this is a 4th degree Taylor polynomial. What's the value of the 4th derivative of f? So again, really important, you find the term with x to the 4th. And according to a Taylor polynomial, this front number is the 4th derivative divided by 4 factorial. So that's why we have 4th derivative divided by 4 factorial set it equal to that coefficient 6. You're solving for the 4th derivative, so you get 6 times 4 factorial. So that's a very common application as well. And then the back of this is our error. So you have alternating series, error, which is the next term. And then this is the problem that keeps coming up, or a variation of it. You have f, you have centered at a, you have nth degree, so it's a degree 2, and they give us an interval for x. So we take the derivatives using the chart, and because it's n is 2, technically you go down to the second derivative. But I know that they're probably going to ask error, so I usually try to do the next derivative, but I just don't plug in. I just get the derivative. Take these guys, plug them into the numerator of all the terms, and you get this Taylor polynomial. Part B says use Taylor's inequality to estimate the accuracy of using this 2nd degree Taylor polynomial versus the actual function. So that's where we're using this Taylor's inequality Lagrange error bound. Because it was a 2nd degree Taylor polynomial, we do 3, 3, and 3. So again, it's the next number. This is the 3rd derivative divided by 3 factorial, and then x minus 8, because it's centered at 8, and then it's cubed. So this derivative, again, we found that here. We didn't plug in 8 for it. We just left it, and that's what you plug in. So 10 over 27 c to the 8/3, and then drop down the 3 factorial. I'm always guilty of forgetting the factorial. And you're trying to maximize error. So we talked about this a lot yesterday. This is in the denominator. So to maximize, you use the smaller number. This is in a numerator. So to maximize, you use the larger number. So that's why we plugged in 7 on the bottom, but 9 on top. Straight to the calculator, you get this. That is not to be confused with the review this problem. So this problem keeps coming up. And then Jesus, I'll go back to 47. So again, the one I just went over with error is not to be confused with this guy. So 57 says the function f satisfies this condition where the derivative, the nth derivative, is always less than or equal to a constant 4. And it says when the 3rd degree Taylor polynomial, so that's why I have r sub 3, centered at 2, so that's why we have x minus 2, is used to approximate f of 3. So this is strange because this is the 3rd degree Taylor polynomial. That number 3 is different than this 3 here. This could have just said f of 5 for all we care. Like it could have been any number, f of anything. But this 3 is because it specifically said 3rd degree Taylor polynomial. So because this is a 3rd degree Taylor polynomial, we use the number 4 here. And this is strange. This guy is less than or equal to the number 4 because it says the derivative is always less than 4. So that's why we plugged this 4 in here. This 4 factorial just got dropped down. And then we plug in 3 because of this. So that's important as well. Sometimes it won't give you this piece. Instead, it'll say, what was the notation? Like, it'll be like f of 3 minus t sub 3 of 3, like that. So that's another way where this is the actual value and this is the approximated Taylor polynomial value. And this represents error. So if it looks like this, then that's we take that 3 and plug it in here for x. So it just depends on how the problem is worded. Anyways, so at that point, it just becomes 1/6. sometimes the problem will say, like on the AP exam, they'll say like show that the error is at most, and they'll give you a fraction. And so basically you just do this process and you go, oh, look, it's less than whatever fraction they provide. It's always rigged to work like that. Okay, Jesus, you asked about 47. Okay, so 47 is that integral problem because it gives you ln of 4 minus x. So since we have ln of 4 minus x, that's equal to the integral of 1 over 4 minus x, but because the x is negative, we put a negative in front. Drop down the negative, and then we have integral, and then we take this guy, and we need it in the form of 1 over 1 minus x. So that means we factor the 4 out, so you have 1 minus x over 4. I pulled this 4 to the front, so it's negative 1/4. Then we have the integral of this thing. And this can be written with sigma, and then we say x over 4 to the n. So at this point, this is really x to the n, 4 to the n. When we integrate, we add 1 to the exponent, so n plus 1. We divide by that new exponent, and we also drop down this 4 to the n. Last step, you solve for c, so you plug in 0 for x, you get ln of 4, plug that here. And finally, you can leave your answer like this, or if it's multiple choice and they have n as 1, then for all the n's, you plug in n minus 1. So again, if it gets shifted from 0 to 1, then you do n minus 1 for all the n's. But if it goes the other way, you would do n plus 1 for all the n's. And finally, it wanted the radius of convergence. So you find, like in this format, this would be geometric. So you'd take this x over 4, that's your r, put the absolute value, set it less than 1, like that. Yeah, it's anywhere I think that it's quantity to the n is where I've noticed it's working as far as like a shortcut instead of having to like do like the root test or ratio test again. Which again, we could totally do the ratio test with this. I was just trying to make it faster. So I've been noticing that anytime you have a quantity to the n, it like you can just use it and it works every time. So yeah. I mean, I probably shouldn't be teaching that. Like I should be teaching like do the ratio or root. It's just making the problem so long. Finding the radius of convergence. Anytime you have like quantity to the n, like if you look back in the problem, if you have quantity to the n, if you take that quantity and set it absolute value less than 1, it helps you get to the radius of convergence like quick.
That's the shortcut.
Yeah, because the long way would be taking this thing and doing the ratio or the root test and working it all the way down. That's way longer.
Did you already do that a couple times?
Yeah, when you just had to do the interval, but this is like you've already done all this work. Then you need a radius of convergence. You're like, ah. These are far out problems, I tell you. That's why it's at the end of the whole class. That's why we don't do it in the beginning. All right. So I put a 2-hour time limit on the test. I don't think it's going to take a full 2 hours, but I definitely don't think it's going to be as short as the last one, just because, again, some of these, like these problems aren't real straightforward for some people. Yeah, people were asking last walk, they're like, when do you know when to use the chart? When do you know when to use the 9.10 handout? So it's kind of tough. The handout, definitely if you have a composition or a product, the handout is great. If it's centered around a number other than 0, typically you got to do the derivative chart.
Um, you keep throwing in a bunch of differentiations, like fill it off.
No, I just, in the last problem, honestly, I just want to give like one nice little review problem. And I don't want it to be some obscure topic from like, you know, something super random. So I try to do like a derivative or an integral. So you can probably
That will be the other question, right?
expect another random review problem at the end. What did you say, Jesus?
That will be the only question that I'll get right.
No way, you'll get others right.
Honestly, honestly, don't know if I can have this year. Like this year, like for my AP classes, I don't know if I'm gonna pass it, maybe barely, but like for calc,
We have a long way. Don't
not looking too
don't
good.
stress out about the AP exam just yet. We have lots of review, and the review is good. The practice exams, if you take the practice exams seriously, like they're so helpful. That's what kids always tell me.
Because
Because
like whenever I do the homework and the test, I have to like depend on the notes because I never had to do that before. It's like
yeah,
help me gain understanding. And relying on it, I'm like,
yeah. So when you start doing the AP exam review, I would start trying to do things a little less reliant on, you know, notes. Obviously, you have to look things up. Believe me, I've been looking things up in this chapter, the whole chapter. But in general, you know, think about an AP exam. It's like more holistic. It definitely like you, when we do practice exams, you'll start to be like, oh, that's how, you know, you see very familiar problems. It's nice. So. Yeah, I know, it's crazy. Yeah. All right, I'm gonna stop recording.